All right, here's 7-6, day 2. You're going to notice I've filled in a couple things since we left off in 7-6, day 1. Because we're working on the same 2 problems. But it's time to graph. So the things you're going to notice are I took a couple of those constraints that we wrote and I solved them for y. And I got my scale factor set on my graph. Okay, so basically, we're ready to graph. So before we do this, 2 things I want to point out. At this point, it becomes just like a problem like section 5. That's all it is. Okay, we're graphing a system of inequalities. In the previous section, that's why we practiced. Okay, the second thing is what we're after, and it's the corner points. Okay, we've talked in day 1 about how the corner points are the possible solutions. In this case, it's the maximum profits based on how many caramels and almonds that we produce. Okay, that's what we're after. In the other problems where we tested corner points, we already had the graph and we already had the corner points. The deal now to truly do a linear program from start to finish is we got to produce the graph ourselves. And that's going to be something that we're expected to do. All right, so constraint number 1 had a y-intercept up at 1200. I'm just going down 1 over 1 because it also had a slope of -1. That's a 1200 there, even though it doesn't really look like it. You can only see the 120. The screen's cut off a little bit, but that's where I want to be. All right, there it is. Sorry about the squiggles there. You might notice with it writing on the iPad like this, drawing a truly straight line can be a little bit trickier to do. You'll probably have better luck with paper and pencil. But keep that in mind. These all should be straight lines. All right, so I'm going to label that this is constraint number 1. You'll see later on why I want them labeled. And then if I were to test the point 0, 0, I would see that I should shade over here. Okay, 0, 0 would be a solution. So I'm starting to build what we call our feasibility region. Okay, everything would have to be inside that triangle to possibly be a solution. Okay, as we're working towards the feasibility region, don't forget that the x and the y-axis are also constraints. They always form potential borders to the feasibility region. Okay, I've got them marked on there with black lines. Those count. Okay, that's why I said I have a triangle, because those axes are forming 2 of the 3 sides. All right, next one is going to be 0, 0 with a slope of 1/2. I probably skipped over it a little bit too much, but notice how I solved, these are all lines, right? Linear programming, duh. I solved them all for y. Just think like when we graphed linear equations, that's the form that we want them in to graph, all right? And that'll be a thing because when you write the constraints, they may not be in that form, okay? If they're not, switch them. Here, constraint number 2, when I wrote it from the written description, it already was. So I didn't have really anything to do with it. So here's constraint number 2. And note right here, see where those 2 cross? First of all, I would shade down here, by the way. I should have. This is an interesting one. We couldn't use the point 0, 0 to test, so I could test, pick one of those points along the x-axis, like 200, 0 or 400, 0. Just plug any of those in. You'll see that they work, and they give you a solution, so I would shade underneath it. Where those two constraints intersect, make note of that. That's a possible corner point. No guarantees that it is, but it could be. Okay? Last one here is a little bit tricky. Okay, so normally I'd want to line up its y-intercept. That's negative 200. Okay, that's not on my graph. But now use its slope of a third. If I came up 200, okay, keep thinking of a third. If I came up 200, I would have to go over 600. So I know that point at 600, 0 will be on this line, the line that forms the inequality. So up 1 over 3 and we would get this. Okay? And if I tested the point 0, 0, it would say to shade, this is constraint number 3, by the way, to shade above it. Because 0, 0 would be a solution. And here's what we have. If I go off the arrows, and notice how I'm stopping at the x-axis, here is what we call our feasibility region. Okay? The points in that region represent combinations of chocolates. X for caramels, Y for almonds. Okay? Here's the really big thing about all those points. Okay? The paragraph of information described all these constraints that we have to work within. Take the first one, for example, that we can only box 1,200 we can only produce 1,200 boxes of chocolate each month. With those points, I don't have to worry about it. Okay? I know they work. They meet all the constraints. There's a corner point. There's a corner point. There's a corner point. And there's one. Okay? There's no guarantees we'll always have 4. But you'll see the 2 that we'll do today, they do. They both have 4. Now check this out. 0, 0. So you might be looking at that thinking, produce nothing? Well, okay. The fact that it's a corner point means it could possibly be a solution, but this is a maximization problem. So we know that's not going to be it. We're not going to make our max profit from doing nothing. Still check it, because I don't want you to use any discretion about checking corner points. If it's a corner point, check it. Okay? You probably know right now that's not going to be our solution, and that's okay. But when it comes to corner points, I don't want you thinking about it. Check them, right? Because it technically could be any of the 4. 600, 0, 800, 400. That seems like a really, I can actually tell. I know that one's going to be better than the other 2. That might be it. Now, way over to the right, look at that. Look at that corner point. Okay, it doesn't really fall on one of the corners really nicely, so I can't actually tell what it is. Okay? This is why you label them, because I can look at that and see that is where constraint number 3 meets number 1. And this, as a matter of fact, takes us right back to section 1 or 2. Okay? I'd love to just go off the graph and observe where the corner points are. And you might have noticed, for the first 3, that worked just fine. The last one, it's hard to tell. All right? So I can't get the exact corner point graphically, but I can do it algebraically. Okay? So I set the two I'm using substitution technically that we covered in section 1. Add 200 to both sides, and you would get 1400 over here. Add x, and we would get 4/3 x. 1400 divided by 4/3 would be 1050. Plug that in. I'd plug it back into constraint number 1 and subtract that from 1200 and then get 150. And there you go. Okay? Now, the better your graph is, the less you will have to do that. And there's no guarantees that you'll have to. Okay? So the more accurate your graph, the better. But do keep this in mind. If you can observe it from the graph, go for it. But I'm expecting that you have the exact corner point. So if you ballpark it from the graph, I'm expecting you come up with 1050, 150 exactly. All right, our objective function was 1.5x plus 2y. And really at this point, we've done the dirty work. We just got to check and see. We could make nothing and we would get $0 each month. Okay, I don't think that's going to be it. How about 600 caramels and no almonds? Well, that would be unfortunate, but it could lead to max profit. It would yield $900 each month. So, all right then. Now these last two, these seem like the real possibilities. I think they're going to be pretty close. How about produce 800 caramels, 400 almonds? Way better than the first two. That would give us $2,000 a month. How about 1,050 caramels plus only making 150 almonds? It's close, but if you were to crunch those numbers, you'd see not quite. Our solution to get a maximum profit each month of $2,000 would be to produce 800 boxes of the caramel chocolates and 400 of the almonds. All right, so here is the one with the sports drinks. All right, so from what you have from the first day, notice that I solved the constraints for y, and I have my graph ready to go. Okay, that's what I've got. That's what I've got. All right, so let's just dive in and let's graph. Constraint number 1 states, one heads up on this one. If I do it well, and I got to try to make good, nice graphs here, that whole deal on the last constraint on the previous one, we shouldn't have to do that. This should be, with a good, accurate graph, we should be able to just simply observe all 4 corner points. So first one is 5 minus x. So start at 5. Slope of -1. Here's constraint number 1. All of these are greater than, so you could test the point of 0, 0 on any of them, and you're going to see none of them are going to work. Okay? Here is 6 minus 2x. So that would go there. Now here, if I had been a little more accurate, I should notice that there's going to be, those two constraints are going to intersect right there. Okay, so that is something to definitely make note of. Hopefully my graph is accurate enough to show it. constraint number 2. All right, and then 3 is 3 minus a third. So down 1, I'll start here, down 1 over 3. It does look like right there it intersects as well. That one was a little better. And of course we'd shade up there, which would give us this unbounded feasibility region all the way up here. Which, if you think about the fact that this is a minimization problem, that actually makes sense, because you know, if you wanted to meet the vitamin A, vitamin C, and calorie requirements, just drink more, right? Whether it's cup or you know, drink X or Y, if you just consume more of it, you'll eventually hit them. Okay, we want to do it for as cheap as possible. Okay, that's where the whole linear programming part comes in. All right, so there's one here. Once again, don't forget about the X and Y axes. They always form boundaries. Okay, this one I didn't do a great job in constraint number 2. Good enough. If you produced a really, really accurate graph, you would be able to observe that's at the point 1, 4. So I should be keeping track of these. That I have 0, 6. I have 1, 4. That one I did a little bit better job of, and you can pretty clearly see that's at the point 3, 2. So that's a point I want to check, and then I also want to look at 9, 0. Okay? Good, accurate graphs on graph paper. If you don't have any graph paper, by the way, keep in mind the Moodle page has a link down at the bottom of Chapter 7, and you can print off as much as you want. Got, obviously, you know, whatever you need, take and print. Good, accurate graphs on graph paper mean you're more likely that you can just see the corner points on the graph and you don't have to do any solving with substitution or potentially elimination, though it would probably be substitution. So keep that in mind, okay? Mine was okay, right? It was just okay. Now, one thing before, because we've really done the tough stuff. We've got our graph, feasibility region, corner points, and we're good. It looks like, you know, right here, check this out, you know, why weren't we interested in 2 and 2.5? Okay? It's where 2 constraints intersect. All right? What I want to bring up here is that a corner point is where 2 constraints intersect, but it has to be on the boundaries of the feasibility region. Okay? That didn't make the cut, because that looks like it is where, I suppose I didn't label constraint number 3, did I? That is where 2 and 3 meet. Okay, that is where constraint 2 and 3 meet. But it's outside the feasibility region formed by 1, which was the calorie constraint. So what's going on there, and the reason we didn't check it is, it meets the requirement for vitamin A and C, but that combination does not provide enough calories. There was a minimum amount that we said, and I think it was like 300, and that doesn't get it. All right, so it's not a point that we checked. The corner points on the edge of the feasibility region, we don't have to worry about it. We know that they meet all the constraints. So let's keep moving on. We've got our 4 corner points, and that is really what we wanted from our graph. If we go back to our objective function, I believe it was 12 cents for x, 15 cents for y. All right. Oh, no x and 6y. You can do that for 90 cents. We'll see if we can beat that. What about 1 of x (4 cups of y). It's better, quite a bit better actually. Remember, this is just cost per person, so think if this was somehow being provided to a large group of athletes or something like that. This is cost per person, so this number could be multiplied many times over depending on who these sports drinks are being purchased for. Three and 2. Get it all the way down to 66 cents. That seems tough to beat. We have 1 left. Is the solution to not buy any of y and just do 9 cups of x? Turns out no. Not only is that not our solution, it is actually the most expensive way to do it of the 4 that we checked. So, just to wrap this up, 3 of x, 2 of y would lead to a minimum cost of 66 cents per person.